David, start with you. Are you a proponent of string theory, an adversary? Are you agnostic? We'll start, even before we know what string theory is, we're just going to take the temperature.
So I've been cohabitating with string theory for almost 50 years.
Out of wedlock.
Yes, out of wedlock, but never divorced.
And so the temperature taking there is, I'm going to call it agnosticism, but you can argue with that.
No. So I've noticed a lot of changes over the last 49 years in both me and string theory.
Clifford, temperature taking. I also want to, so Clifford's going to be signing his book afterwards, and I just want to mention, because it might not come up in conversation otherwise, that he also drew his graphic novel, which is quite amazing. Woo! So, yeah, we were discussing this while you were, in some sense, teaching yourself to draw even better, so that you could rise to this challenge of the book. And I know you discussed some of these ideas towards the end of the book, but are you adversary, advocate for string theory? Neither.
Scientists are, I think, historically, we learned that in some ways the best way to be is pragmatic when it comes to doing science, and you work on the best. You work with the best tools that are available at the time. If something better comes along, you can drop those things and move on to the next thing. Right now, string theory remains, for the kinds of questions we think we understand to even ask, it remains the best shot at answering some of those questions. And so, it could turn out to be wrong, but until something better comes along, that a lot of people work on it for that reason, and I'm one of them.
So I wanted to get us into even what string theory is. This famous film, which people might recognize from 1977 by Charles and Ray Eames, it's a Power of Tens film. You're not freaking out, I've drastically sped it up. We're going into the galaxy, powers of 10, you can see on the right and the left. We're scooping in really fast past the solar system. We're going to come into the city of Chicago, where they're having a picnic on a famous lawn. And I figured we don't have the attention span that people did in 1977, so I had to triple the speed. Now we're going in to his skin by powers of 10. And this is really the scale at which we're thinking. The world looks solid, right? But we know famously it's not. You think about those examples. Here we're going into a white blood cell. We're going into the organelle, into the cell nucleus, into the DNA, and then into the actual atoms of the DNA. This film is still so beautiful. And I think it was narrated by Philip Morrison from MIT. And we're coming into the sort of blur of the motion of the electrons in the atom of a carbon atom. We're coming into the nucleus of the carbon atom in a second. And now we're getting down to the scale that we're really talking about, 10 to the minus 14, 10 to the minus 15 meters. And here we are in this bizarre world, right? So what this sort of frame brings up is, to my mind, three things. One is that the world is not solid in the way that we're familiar with in our intuitive experience. Two is that there's particle physics. So before we talk about string theory, we should at least mention why there's particle physics, that at the subatomic level there seem to be fundamental particles. And three, the quantum level. So does anyone want to tell me why we care about particles? What are fundamental particles, first of all? Let's just do a 1-minute primer. David, go.
Quarks and leptons, and that's it. Plus a Higgs.
But there are a lot of quarks and leptons. There are a lot.
More than one ever expected.
Right, so if a quark and a lepton is at the fundamental constituents of particles, which is what we thought prior to string theory.
At the scale you stopped at.
At the scale I stopped at, exactly. So what does it mean to be a quark? It means to have a certain mass, a certain charge, certain quantum properties, and that's what it means. All electrons are identical to all other electrons. There are no fat electrons or light electrons. There are no electrons with any history. They're all absolutely identical. But yet there's this proliferation of particles.
Yeah, so
can you express that concern?
So, the quest is simplicity, right? So you're breaking things apart and you're trying to find the answer to that quest. Can I make all this complication that's us out of much simpler building blocks just put together in different ways? And it seems a really great quest, and it works amazingly well. But what you end up with is a lot, as David said, a lot of building blocks, not just a few. And so you begin to wonder
it's
whether...
not that many. Remember, we're constructing the whole universe.
Fair enough. But it would...
We only have, you know...
It's like an alphabet. It's an alphabet of
for
particles.
everything in this room, we just have 2 quarks and 1 electron, and that's it. So we physicists are pretty greedy. We'd like to explain why there are 6 kinds of quarks and 3 families of leptons. But come on, everything in this room, all of the physical objects in terms of just 2 quarks and an electron.
That's amazing.
Pretty amazing.
That is amazing.
So let's stop and appreciate
we should appreciate that. And of course, you got the Nobel Prize for figuring a lot of that stuff out. So on the other hand, there's a huge amount of matter that we know exists in the universe that isn't made up of any of that stuff. So that's one thing. And then the other... That's dark matter. And then the other thing is that even if we have this list, and it's a very ordered list of particles, there are patterns in that list that have no explanation. And as David said, we're greedy. We want to understand those patterns. So why are there 3 different there's an entire family, so there's 2 kinds of quark that make up most of what, the
most of the nuclear particles.
The up and down quark, and then there's the electron, and then it has a cousin called the neutrino, and that's great, but then there's another identical family just like that, but heavier. And then there's another one heavier, which we don't really seem to use very much, but it's there. Why? So it isn't so much the number of these particles that we come down to, but what are the patterns that underlie them? And that's really not understood. And if there's a pattern, there's usually a reason for it.
No, it is actually, not to digress into too much aesthetics, but it is amazing that essentially all of the forces that control matter, all of the matter forces that control everything in the universe that we know of, look like they can be unified into one very elegant theory. And that's, of course, what motivates a lot of this pursuit of simplicity, is that it's worked so well. Mm-hmm. This has worked, and it was pretty stunning when it worked the first time, then the second time, then the third time. So if the entire universe is describable by matter forces on one side, all of which can be elegantly unified, and gravity, the outlier, right? So the real desire, in addition to doing what you're describing, Clifford, which is making the list of cocktail ingredients seem simpler or somehow more motivated, there's also gravity as the outlier. Mm-hmm. And is that... Sorry about the handheld mics. We're like lo-fi here. Yeah.
So the amazing thing is that I got almost 40 years ago, both of those ideas came together when the standard model, this theory of quarks and leptons and the matter we're made out of, was completed. And people tried to do 2 things. They first took these various forces, pieces of a jigsaw puzzle if you want, and fit them together. And they found it was easy to fit them together without any missing pieces. And second, they took the theory of these forces and extrapolated it to a billion times past that distance that the film stopped at, and discovered that those forces look like they come together at the same scale of distance where gravity becomes a strong quantum force.
Yeah, that does kind of give me chills.
That's kind of a miracle.
It is. It gives me chills. It's kind of amazing.
This has been, for me, for the 40 years of my life, scientific life since then, the most important clue. And for many of us. Because, my God, that's a signpost, a kind of a message from nature that unification with gravity is achievable. Mm-hmm. Hasn't worked out so well.
So before we get to the failures, the one analogy I like to give for people is that we look at something like steam, water, and ice, and they could seem fundamentally different, but we realize they're just different phases of the same thing. Steam's higher energy, water's lower energy, ice is the coldest. But if we look at all of them in some limit, we realize, oh, it's all water. They unify. And so in this sense, all of the matter forces look different, but in their very early universe, they might all have just been the same thing, including gravity. And that's this very high energy scale that you're describing, much smaller scale. This is my incredibly sophisticated graphic of a string theory. That took me surprisingly long, really. Really disappointing way to spend my time.
But before you get to that,
please.
It's important to realize that although it seems like a theoretician's dream, right? You do the extrapolation, and it's wonderful, and it's very suggestive. We have hints that it's on the right track, right, from experiment. And the amazing discovery in 2012 of the Higgs Boson is a huge example of that, because part of that unification, where the force of electromagnetism and what's called a weak nuclear force come together, that predicts a certain kind of particle. And that's what you always try to do. You have a theoretical idea, and then you work out the consequences of it on paper, and then your experimental colleagues go and find it. And one of the predictions was the Higgs particle. And so the reason why that was such a triumph was precisely because it not just tells you about the origin of mass and what have you, which is important of elementary particles, but it tells you about this unification scheme really being a reality.
This is very perfect because I happen to drop this in there. So
there you
this
go.
is the Large Hadron Collider, which is or it's an instrument in the Large Hadron Collider which discovered the Higgs particle. Several billion-dollar experiment that was built to look for this mysterious particle. And so, David, you already pointed it out. Why can't this detector, which is phenomenally the most powerful accelerator ever built by humans, possibly that ever will be built by humans, why can't it probe all the way to the incredibly high energies that you said were a billion times higher energy than we stopped in the film? Why can't we go there with this?
It's what I call the curse of the logarithm. That requires an explanation.
Indeed.
So that holy grail of physics, which actually was identified by Max Planck, the inventor of quantum mechanics, the Planck Scale, which everyone agrees is the fundamental scale of physics based on fundamental
Is that
units.
applause for Planck?
Let's hear it for
Yeah,
Planck.
he was pretty smart. He was pretty smart.
Planck's in the house.
Is a distance of 10 to the minus 35 meters. Nanometer. My God. And but for theorists like Clifford and me, it's easy to do thought experiments at those distances, because from the scale where we have direct experimental evidence about what's going on to that incredibly short distance scale, things vary. Physics, the phenomena vary very slowly, like 1 over the logarithm of the scale. If you forget what a logarithm is, it just...
It's just a nice function.
It's a nice function. But when things like the scale are varying a lot, the logarithm is varying very little. So nothing much happens to our theories that work so well when we go to these very short distances. So without any trouble, without any calculational trouble, we can extrapolate. On the other hand, the cost of actually doing experiments, of building these incredible machines to explore these very short distances, increases like the energy, or 1 over the distance squared at least. So physics doesn't change, but physics changes very slowly, but the cost rises very sharply.
This is an accelerator which is like a ring like 27 miles around, right? So you're smashing things together after speeding them up in this 27-mile accelerator. You'd have to have something, the size of the galaxy to to the scale.
It's unimaginable.
Yeah, so we'd have to, you know.
I have faith in science and technology, but so far we haven't. You know, can't even imagine exploring directly the scale at which it would be apparent to everybody that strings were there.
Okay, so here we are. As you said, you know, it's not that bad. We have a couple of quarks and an electron, and we make everything in this room. So here's my question, Clifford. String theory, why? Why?
Well,
why do we need it? Why can't we stop with the particles and be happy?
So this is one of the reasons why string theory is appealing, because there are many different things that we've talked about that a priori aren't necessarily connected to each other. That string theory at least seems to have a chance of addressing. And so when you can address lots of different questions in one framework, that's really great for a theorist, because it means you just have the one toolbox. So one of the sets of questions that I talked about earlier is the fact that there are these weird patterns. You know, why? You know, I have this family of particles that we're made of, but there's another family of it just the same but heavier, and then another one just the same but heavier. Why is that? So that's one sort of question. Then there's a whole business of the universe is intrinsically quantum mechanical. We use quantum mechanics to figure out those particles. We don't have a quantum mechanical description of gravity. The best we have is Einstein's equations so far, which are classical in the sense of non-quantum. But again, string theory, for reasons that we might get into, give you a very elegant way of describing phenomena that are gravitational in a quantum mechanical way.
Can I play my role just as paraphraser, and then you jump back in? So when we're talking about gravity, we're thinking about gravity is synonymous with space-time. We're thinking about the universe on the largest scales. We don't even have to call it gravity. We can just call it space-time. And we're thinking about how it curves and warps in response to matter and energy. And the fundamental problem that you're referring to is the fact that we don't know how to see that as individual bits of space and time. Quantized, quantum bits, little individual bits.
If that's the way it works out.
If it works out.
There may be other approaches to quantum gravity that tell us that it isn't. You know, what we naively think because of our experience with particle physics is that when you get quantum, you get little chunks, the particles.
Right, so if I did the Eames film on empty space in the universe, I should eventually also come to little discrete wobbling bits.
That's one suggestion we have. But just to finish the point, so there is a way in which you get something that looks like a quantum description of gravity, and hence, you know, space and time itself, captured in a quantum mechanical way, which we sort of need, not just as a game, but because we need it to understand black holes, we need it to understand the birth of the universe, all of space and time, things like that. So string theory somehow allows you to get at those things because it comes at the questions and the description from a very different angle. And the angle is that you just don't have particles. And if you think about it, why did we stop at looking at fundamental particles? And so various people, for various reasons, started going, well, what if you had, instead of a particle, you had an extended object like a bit of string, and that then vibrates, and maybe far away it kind of looks like a particle, but then the different vibrations give it different character that you might associate with being different particles. And so that's where the idea started. I mean, it isn't really where the idea started, but kind of where the idea started.
What I love about the string theory idea is this idea that all the particles in the universe are the same fundamental string. There's only the string. And the difference between the electron and the quark and the families and the Higgs field and all these things is just different fundamental notes, harmonics played on that single string. Now, David, I know you're itching to jump in here.
No, it's a beautiful idea.
It is a beautiful idea.
And especially the heterotic string. But
Invented that.
But it's only one way of looking at things. So, you know, the most amazing thing about string theory, or whatever that is now, is how surprising it has been. So, you know, science. The role of science is to understand and explore nature. But as a scientist, when you do that, you continually have the feeling that nature is teaching you things, is informing you, is revealing her secret. I always refer to nature as a woman, I'm sorry. and it might be
I
a little
approve.
chauvinistic.
I approve.
and old-fashioned. You approve? Revealing her secrets, and that can happen in two ways. I mean, the best way, of course, is direct observation, discovery of new phenomena, out in the universe or in your microscope or whatever. But it can also happen by exploring the conceptual framework that we have constructed and tested and used and have faith in and is mathematically strong and firm enough to extrapolate it. And that's largely what has been happening within string theory, actually, for 50 years. And the history is fascinating because it didn't begin as string theory, as you know, as Clifford alluded to. It started out totally
Different motivations.
different motivations, but I, as a practitioner in this field, I think we're learning from this framework. I don't regard it really as a theory yet, because theory should be able to make predictions. It's a framework that is connected to the framework which we continually test at the LHC, the standard model, and we're hopefully, since we can't make predictions and tested that at the moment, we're learning essentially from nature. We're exploring this framework that we have constructed to explain part of nature, exploring its structure and in particular, as Clifford emphasized, the quantum gravity side of it, which we know so little about. So it's an exploration. And one of the ideas, one strong way of looking at it, powerful way of looking at it, indeed is the stringy way. But that's only one way of looking at this structure that we're constructing. We say that particles are made out, that matter around us is made out of particles. And that's also a nice way of talking about it. But again, it's an approximation. We are made out of quarks. You're all made out of nuclei, and those nuclei are made out of neutrons and protons. And the theory I was involved in explained, if you want, how those protons and neutrons are made out of quarks. But nobody's ever seen a quark. It doesn't exist as a free particle zooming through the universe. It is a construct. And in some approximation, which is very hard to achieve, it requires those big accelerators. You can see quarks moving freely for about a billionth of a second. But it's a way of describing, and it's in the same sense of string theory. And to some extent, what we've learned the last 20 years is way beyond that. It's a little harder to picture. It's not just a vibrating string.
You mean in terms of membranes or in terms of
In terms of
dualities?
higher dimensional extended objects, but in terms of very deep dualities between different ways of describing physical reality. And in particular, coming back to what you emphasized, what we're trying to understand here is space-time, the quantum dynamics of space-time.
I mean, that's the real secret goal.
We're beginning to see a way of understanding how space-time itself is an emergent concept from some other way of looking at things. And it's not a space-time is made out of strings picture.
Right.
It's quite different.
Right.
Much
so
more
this is
profound.
Yes, this is lovely, and we're going to, I hope, come back to this as the conversation progresses. So I said, if we did the same thing in empty space as the Powers of 10 film, we would see little bundles of material, and that's the old quantum gravity aspiration. But now we're moving into a new era where maybe, and Clifford, you already kind of said, well, maybe, because you were, I think, preemptively thinking about this, that maybe we'll find out that space-time is actually not fundamental at all, and that the only thing that matters is matter. But that is, we're going to get there. We're going to get there. We're going to get to wormholes and black holes and all what I call the hard stuff. But before we do that, I've realized, speaking of time, I don't have a timepiece. Can I borrow your watch? Sure. Okay, so I wanted to do that very publicly, so it didn't look like we were whispering. And then Clifford, I know that you looked like you had a thought in response to this.
Well, it was mostly, and it's sort of like what lies at the root of the realizations that David was talking about that we've had in the last 20 years. And and unfortunately, popular descriptions of string theory never get to this part. They always get to the, oh, yeah, everything's made of string, and then different modes of vibration are different particles, and that's an awesome picture, and then, there's pictures of violins and guitars, and it's wonderful. And that basically was, the 80s. And a lot has happened since then. There's a reason we stop at that, but that's a beautiful picture, and then it seems to just get more complicated and more confusing. But you're a sophisticated audience, so let me say it. What we realized just when I said, why did we stop at particles? Why, a particle has, in the language we use, it's a zero-dimensional object. You just say where it is. And then a string is a one-dimensional object because you need to also to say where along the string you are. So it's like a loop or just a string that's moving around. So, give me a second. Why stop there? And so one of the things the theory told us, we didn't put that in, the theory just kept telling us you need to do this to finish the story, is that you don't stop at strings. So then it turns out you can have a membrane-like object, like a sheet of paper. Instead of just a piece of string, you have a sheet of paper. And then you can keep going. And string theory famously has more than just the 3 dimensions that we live in. So you can fill those dimensions more and more with higher dimensional objects. Those all come into play when you fully understand string theory. So, the famous remark is that string theory actually isn't a theory of strings. It still gets called that. Mm-hmm. But really it's much more. And then it's the physics of understanding those different kinds of extended objects that give you this wonderful picture that we've been uncovering, where you realize that, we just got the whole thing wrong. It isn't just some space-time with things moving around, and then you find that description and you go home. It's just that there are different regimes, there are different kinds of questions you ask, and then which set of things you use to answer those questions changes. So sometimes you use strings, but sometimes you use those membranes, and sometimes you use other things, and it's a much richer picture.
And sometimes 11 dimensions, sometimes
right, so
10,
perfect.
sometimes 4,
I love when you do this.
Sometimes 1.
Yes, I love what you. Perfect, David. Thank you. I'm going to ask you this.
We didn't rehearse this.
We did not rehearse this. I hardly tell them anything when they show up. I just show up. So this is the cover of Flatland, a famous book that was published in 1885 by Edwin Abbott. That really is his name, Abbott. I don't know why. And it was a sort of satire, not only of Victorian society, but also an investigation of mathematics and dimensionality. And you see here's point land, which is just a dot, and then here's line land, which is just a line. And his characters live in flatland. They're just 2-dimensional. And one of the things I want to just point out about flatland is if we're looking down on them from our privileged perspective in 3 dimensions, but they have no idea of an up or down, absolutely no idea. But notice how the 3rd dimension, up and down, is everywhere. And we're about to start talking about extra dimensions, which is where you're about to go. And when you think about, we live in 3 dimensions. We have up, down, north, south, east, west. So where are the extra dimensions? They're everywhere in some very profound sense. We just can't point to them. But one other thing I have to say about flatland is the higher up you are in society, the more sides you had as a polygon. So the high priests were circles. Our hero is a square. He actually authored the book. And women were lines, yeah. And they had, but it was and he was actually quite a feminist. But the women had the privilege of being able to occasionally murder their husbands accidentally by piercing them when they came in the wrong door. But enough about politics. So now we can talk about extra dimensions because we can think, suppose you live in Lineland. And it's so small that you think you just live in 1 dimension, but then you realize you live on a straw. And there's this extra dimension, and it's just small. It's literally wound up small. And that's what we're imagining for string theory. So, David, do you want to just at least mention why in string theory we're required to think about these extra dimensions? This is a picture that's often shown with no explanation, and so I won't provide one either. David might, if he's so inclined.
That's a picture of a particularly beautiful structure of 6 extra dimensions, a little Calabi-Yau manifold at each point. Anyway, it's quite gorgeous.
And notice how they're everywhere. I mean, that's sort of the idea. The extra dimensions exist at every point in our three-dimensional space.
Well, it's
There's
not
the
every,
extra
you only
dimension.
have 1, 2, 3.
Yeah. The imperfection
get
of drawing
the idea.
space-time.
Yeah.
So, but David,
So, you
why,
know, look,
why do we need extra dimensions?
came into physics not with string theory, but very shortly after Einstein's theory of gravity, which was a dynamical theory of space-time. And then the big goal was to also unify. I mean, that was Einstein's, spent 30 years unsuccessfully trying to unify gravity and electricity and magnetism. But one of the ideas he pursued and was invented by a Polish mathematician called Kaluza was that there was an extra dimension, just like the kind of circle that Janna showed, you know. And discovered that if you took gravity in 4 spatial dimensions and compactified, made one of those dimensions a very small little circle, you'd get, in addition to gravity, electricity and magnetism. Einstein loved this idea.
I love this idea.
It's
I still work
beautiful.
on this sometimes.
Yeah, absolutely. And Einstein tried, well, it was one of the ways he tried to unify the forces of nature for many years. But this was, so once you understand that space and time are dynamical, then the possibility is there that unlike Newtonian, unlike Newton's theory, they weren't just rigid, immutable objects that, you know, a priori existed somehow in the universe. They were dynamical objects like everything else, and their structure and is open for physics as an open question that physics has to decide, including their global geometrical structure, whether each dimension couldn't be curled up. That's a possibility. In fact, it's a solution of Einstein's equations that determine the structure of space and time.
As soon as Einstein starts
What
punishing, you
happened
ask
weirdly
free.
in string theory was that in string theory, there's much less arbitrariness. One of the great features that attracted many of us to string theory was that you don't have the freedom to decide what kind of space-time you're going to live in. That's dictated, and it turned out to be more than 3 spatial dimensions in many solutions within this framework. So that's how extra dimensions were then discovered.
You know,
if you want.
Yes, please.
Yeah, that's worth emphasizing. It's another reason why, again, you know, string theory could turn out to be wrong, and 10 years from now we're working on something else. But right now, another of the things that got people super excited was precisely that feature. In the history of writing down very sophisticated theories of particles moving in various dimensions, you could actually choose, you could go, I'm going to write this kind of theory in, you know, any number of dimensions I like, just as a game, and you'd get answers, and it'd be an interesting mathematical game. String theory was the first time where we wrote down a theory and we said we want it to live in a certain number of dimensions, and these strings have to move around, and they must obey the rules that we already know nature likes, which is that it has to be relativistic and quantum mechanical. And you put those 2 ingredients in, and the theory comes back and it gives you a list of demands. And theories didn't do that before. It comes back and it says, I'm not going to work unless you work in, you know, in the version that's most well understood, unless you work in 10 dimensions and unless you describe gravity. So we put that in. We didn't ask for it to be in a fixed number of dimensions. And we didn't ask for gravity. It came back and told us gravity has to be in the game. and you have to have a different number of dimensions than you thought. And that was just historically, and even at the time, was really shocking.
I can ask you then, why isn't that an observational fact that disqualifies string theory? After all, every day billions of people verify that there are 3 spatial dimensions, not 11. You don't accidentally turn left in the wrong dimension.
Right.
So why aren't we saying, string theory's dead?
Yeah, right, and you go, and so that was one of the things, right? For a while, people thought those were bugs, and now we know that they're features of the theory.
So why can't I stick my hand?
Because whenever you do a piece of physics, you have to ask what scale are you doing it at. And so one of the possibilities is that you've just been looking at the wrong scale. So various kinds of things, various kinds of processes in our everyday lives have not been able energetically to probe those apparently hidden dimensions. That's the idea.
Because they're small.
Because they're small.
I often think of it as my hand is too big.
It would require the 10 trillion to the trillion to the trillion accelerator to see those.
So if we built that accelerator and we smashed some things together, some of the debris might disappear into the extra dimensions.
People whenever anyone designs a new experiment, or even the current experiments, there's a whole class of theorists whose job it is to look for what would be the signatures of stuff disappearing into extra dimensions. And so that's a possibility. We look for it, we haven't seen it yet. I should mention one other thing. We've gotten more sophisticated now because of brains, because of extended objects, and there's a new way in which we could also have missed higher dimensions.
Unfortunately, because of the curse of the logarithms. Unlikely.
But it has to be mentioned, and that is that, in fact, those dimensions could actually be big and not curled up, but we're just made of the wrong stuff.
Stop it, Clifford.
Yeah.
Look.
Sorry.
Wait, look, this is the Hubble Deep Field. Okay, so hold on, I'm going to skip the Hubble Deep Field. I show it too often.
Okay.
Okay, you can take it from here.
Right, okay. So
it's like jazz, I do my solo.
Exactly, right. So now for my avant-garde solo. So the idea is that maybe the stuff that we've been working on so far, the kinds of matter that we're made of, the kinds of matter we can observe, or what have you, and the forces that govern those things only intrinsically operate in 3+1 dimensions. But then there are other forces that maybe operate in higher dimensions. And in fact, one of the things we discovered in string theory is that it can very readily accommodate that sort of arrangement of things. So it's another possibility, not that those dimensions are small, but we haven't been probing them with the right stuff.
So this is the idea of being confined to a brain, a membrane that floats in a higher dimensional space. The space is large, but I can't point to it because I'm glued to it. I stick to it in some way. Yeah. And to get off of it requires way too much energy for me to break off the brain and punch into the other dimension. Yeah,
or you could interact with stuff that freely moves in that direction, but the interaction isn't very strong as far as we can tell.
Now, is it only string theory that requires us to think about brains, David? I mean, do you think that brains are interesting, the idea of higher dimensional spacetimes, independent of whether or not we look at a billion million times smaller that they're strings?
String theory has thrown up a whole bunch of new ideas, but they can then, for example, supersymmetry, my favorite, unfortunately, not yet discovered, but then have a broader. Once you have new ideas, you can, it's like children, you can cut the ties with the parents. They can go off on their own. And these new ideas have life of their own. So the idea of extra dimensions and brain worlds can be formulated independently of string theory, but it came from string theory. And number two, it doesn't fit into a comprehensive framework that we believe. Eventually, physicists would like to believe that even though they might be exploring phenomena in this domain, it's really consistent with everything else. And so the string theory framework, we have a bit of confidence that we can go way beyond just this phenomena, but it's more general.
So I do want to, you were alluding to dualities earlier, and I had wanted to come back to them later, but I think that this is such a profound and special thing that's been happening in string theory that you were saying, Clifford, that, and actually you were also, David, that there was some excitement that things were foisted on us. we were forced to consider extra dimensions or the theory wouldn't work.
So
And that was
when
kind
you
of, that limitation was
explore,
exciting.
if you're an explorer, you're entering new territory, you have no idea what you're going to discover, and you discover something, they're foisted on you. I mean, it's not that you chose to find the new peak or valley. And
There it
the
was.
same is always true in science. That can happen, as I said, observationally, happens all the time, experimentally, but also in most of the exploration in string theory, unfortunately, to date, has been purely theoretical, speculative, mathematical.
Well, so one of the...
There too, you can make discoveries of concepts and phenomena that you never imagined.
I never imagined. And then there was this moment where the opposite happened, where all of a sudden there were many different string theories, which were all functioning, so it was taking away from you this idea of I've run into an inevitable peak that I discovered on my journey because now there are so many string theories. But this is where dualities are interesting. Do you want to maybe mention how it turns out?
No. So in the beginning, in the 80s,
The universe began in the 80s, in case you were
That was the
confused
second
about
beginning.
that was the second
the Big
beginning.
Bang, 1984.
But for Clifford, it was probably the first beginning. So there were different string theories, and there were about 5 of them by the end. And I had my favorite. But we really thought there were, different theories. One of them was right, by which the others were probably somehow inconsistent. Not only that, and that would be a real theory. Now, a real theory is something, I have 2 definitions. One is that you can put the theory on a T-shirt.
You mean it's short enough that it fits?
Yeah, I mean the principles, the Maxwell's equation. I can put the standard model on a T-shirt. But you can't put string theory on a T-shirt because we don't know what the equations are. We actually don't. We don't know what the organizing principle is, so you can't put it on any one of those 5 theories. You could not. You could put the name.
Heterotic string.
Heterotic string. You couldn't put the theory on the T-shirt. Second, it turned out that 2 things happened. One, as you say, people discovered ways of transforming one of those theories into the solutions of one of those theories into the solutions of another one of the theories. So they really were all unified. And then there's a very ill-understood M-theory generalization that might include them all in some way.
Now, can I just say that nobody knows what the M stands for in M theory? So
There are different theories.
Ed Witten coined it M theory, and he doesn't know what the M stands for?
W.
People say it's W
down.
upside down, right?
Membrane. Anyway, but none of these are theories in my sense. That a theory is something you could put on a T-shirt and you can make predictions, or calculate things that have been measured and test your ideas. That's never happened in string theory. People criticize string theory by saying this isn't science because the theory should make predictions. So I deal with this in the following way, which I think is correct. String theory isn't a theory, so don't criticize it because it's not yet a theory, it's a framework. What we have discovered recently in the last 20 years is that that framework of string, so-called theory, in which one way of looking at it, everything's made out of little vibrating strings, is not different than the other theory we have, which we use for describing nuclear force, the standard model of everything is made out of little point particles. They're the same thing. And in many cases, now we have 20 years of research into the areas of physics, including gravity, including the standard model, where the same physical phenomena can be described in 2 different ways. I don't know whether you have a lot of pictures, but suddenly, do you have by any chance
Sure.
the
I bet I
picture
do.
of the vase?
Are you kidding me?
You do?
Wait, hold on. We're going to come back to this. How cute is this? I drew this myself.
Not that. You know,
Okay, we're going ahead. Wait. Ignore him. That's my
Black
black hole. Wait, you're going to love it. Is this the vase you were looking for?
no, I'm
Not even
looking
close?
for this great, this picture
mean
of the faces.
Oh, yes. No, that I
You
don't
blink
have.
your eyes, you
Right.
see a vase. Everyone knows
Oh,
this.
right, yeah.
You blink your eyes. So what is it? Faces, vase?
But this is a nice point to talk about it. I actually stole this from Natalie Walkover's article in Quantum Magazine. Natalie, you're here? Woo! Natalie's here somewhere. David, this is relevant. Maybe, Clifford, you could speak to this too, in the sense that this is the hard stuff. I was saving it for the end, because nothing we've talked about is particularly hard yet.
But if I blink
See my face? I was making a sarcastic face. Oh, you can't see it. So, in this illustration, the idea is that there is a model of string theory which describes the world, a world, a space, a time. It has gravity. Things are made on strings and membranes. Clifford, as you said, all kinds of higher dimensional objects. And on the boundary of this space-time is an absolutely equivalent theory which has no gravity, no strings, is purely particle physics, but they're absolutely equivalent. There is a dictionary from one to the other, so that you can talk in one language or the other language.
Strangest possible dictionary.
Now, can I, before I ask Clifford to jump in, as the role of paraphraser, I liken this to a reversible coat. You have a raincoat, which is reflective on one side and cotton on the inside. And there's some things that it does as a raincoat and some things it does reversible. So like if I want to see it on a bike in the rain, I can only see the reflective one, but the thing that I know is that the cotton one must be there too because they're the same coat in some sense. So there's things that I can learn by looking at the particle theory that tell me it must also be true for the string theory because they're the same coat. My analogy is breaking down.
Well, but I like that vase.
Yeah. You could have spared me my long digression.
No, the thing is, with the coat, you can sort of see both at the same time. Right?
Well,
these
I don't know. I button
dualities-
my coats really snug.
Does it have a button or zip?
You pick,
that-
they're-
right, just kidding.
So,
Let
I
me-
want to hear your take on dualities because they are
So-
one of the most gorgeous things that's come out of string theory.
Yeah, and it's from my perspective, it fits very nicely with the history of how we do science, which is pragmatism. And it's to do with this thing that we sometimes get into these heated arguments about what's true and what isn't because we come too wedded to the theories on the page. And we somehow think that the theories on the page are reality, whereas they're just devices for helping us to understand the world. And those devices have limitations. And sometimes it is the case, and maybe in retrospect not too surprising, that you could have a setup where the toolbox you use to describe nature changes depending upon the question you're asking of nature. And I think those are nice words, but what string theory has been doing is giving us exact examples of how that works. And how, there's a whole bunch of toolboxes. And one of them is the old string theory idea that we know, that we put in the popular magazines, which are the vibrating strings and what have you. And then there's some of these other things which I can get to as well. But they all sort of say the same thing. There are phenomena where if you ask this kind of question, you use that toolbox. You ask this other kind of question, sometimes of the same things, but you ask a different kind of question, that toolbox isn't going to work anymore. But you use this other toolbox. Now a good theory, a good framework, and maybe even a good theory tells you when you use which toolbox. And in some ways, string theory as a framework is this whole collection of toolboxes, some of which are strings, some of which are these extended objects called brains. Sometimes there's gravity, sometimes there isn't gravity, like in that picture. Sometimes there's 10 dimensions, sometimes there's 4 dimensions, sometimes there's 2 dimensions.
But it's all the same universe.
But it's actually the same toolbox which we can apply to this universe that we're trying to describe. And the most important lesson, I think whatever happens with string theory, if you told me what are we going to learn that's true about nature from string theory, some of the details may all turn out to be wrong, but I think that lesson that lots of the things that we thought mattered, like the dimension of space-time and how many fundamental particles there are, those will turn out not even to be the right questions. Those will just be artifacts of being at a certain energy scale, asking a certain kind of question. But I think like dimension of space-time, even space-time being this thing that is four-dimensional and smooth and gets deformed in Einstein's gravity, all of that will turn out to be an approximation.
Well, let's talk about our
So
favorite
there is-
approximation.
yeah.
Please, go ahead, David.
Let me just comment on these
Yeah.
dualities. So the dualities are different ways of looking at things. The interesting thing about the dualities that are being explored now in string theory is that they relate perhaps the two most fundamental concepts we have in physics in ways that nobody ever dreamed of. One is space and time. So I always tell audiences that the greatest intellectual advance that any of us make, me, you, anyone, is in the first 6 months of our life, where we, each of us, without much teaching, invent space and time. Space and time, you realize, are not something you directly sense. You've never seen space or felt time. It's a mental construct. It's a theory. It's a framework in which we need, as children, to get from one side of the room to the other and pick up the toy and so on. We construct space and time as our brains are developing. You know, we can't even speak. Our brains are developing and we're inventing space and time. What amazing feat. Very crude concept, however, we've learned. I mean, Einstein has changed it, and now quantum mechanics is. And so space and time, our most basic concept of physical reality. The second, we've learned in the last 100 years, the basic structure of physical reality is a different space called Hilbert space, where we live in quantum mechanics. And we're just, as physicists, I truly believe, learning quantum mechanics. It's a very deep, new way of looking at the world, and 100 years isn't enough to grasp it. We've applied it with enormous success, both basic and practical. Most of our modern technology is based on our quantum knowledge of materials. But we're still getting used to living in Hilbert space. And the amazing thing about these dualities that have been explored and discovered in this exploration of the theoretical framework, which is sometimes called string theory, is connecting those two most basic concepts.
No.
Both trying to, if you want, understand what space and time are made out of in terms of a quantum mechanical system, and understanding the structure of the quantum space in which we live in terms of geometry and structure of quantum mechanics. It's an amazing thing, and I just am in awe of what we are continually discovering. All of us are. It's like children discovering a new world. Mm-hmm. And we have no idea where it's going to lead.
So we started this conversation by looking at the large scale space and time of the universe as we observationally saw it in 1977, and zoomed into the quantum. And then, Clifford, you reminded us that string theory magically brought us back to space-time by helping us understand that space-time was part of the whole story, not just the dimensionality, but the dimensionality of the fundamental objects living in space-time. And so we're at this weird overlap of the large and the small, which you're musing over. And one of the most beautiful aspects is that we can use objects like, this is a black hole. It's not a real picture, but it's a lovely computer simulation of a black hole. We can use space-time on the largest scales like black holes to understand string theory, and to use string theory to understand black holes. Would you be willing to reflect on that for a minute?
Yeah, and there are many reasons why that's an interesting place to do that. One is that it turns out, although you hear things about black holes and they sound very exotic and what have you. It turns out black holes are, I think by almost any definition, the simplest objects in the universe, either in the theoretical universe on the page or even the kinds of black holes that you're hearing about being discovered now explicitly because they collide and coalesce and send off gravitational waves.
Ray Weiss was here last month.
Oh,
we
right.
Talked about
so
it.
You're all experts. Great. So it turns out black holes are incredibly simple. And what theorists love are simple laboratories for ideas. And so it turns out that a black hole is very simple, but it also ends up being at the sort of just on the edge of our best understanding of gravity from the side of Einstein's equations in 1915, etc. They're the simplest, some of the simplest solutions you can write down with those equations. But then also just the fact that they have this thing called the horizon, this apparent place of no return. Quantum mechanics doesn't play nicely with such one-way barriers. And so it tells you that there's an interesting opportunity to understand black holes and hence an interesting non-trivial solution for space-time in the presence of quantum mechanics. And so going back, for example, the reason why Stephen Hawking, one of the main reasons he's famous is because his discovery that that's a place where you can actually learn things without even understanding a full quantum theory of gravity. You can get a profound statement about aspects of a quantum theory of gravity by looking at black holes. So coming to string theory now, even though we're still flailing around to try and understand how best to find ways of describing all of the kinds of particles we've seen and what have you, the good thing is that there's one space-time, as it were, there's gravity, and then you can ask, in the context of string theory, what it thinks of black holes and quantum mechanics. And it turns out to be a relatively simple question that you either get right or you get it really wrong. And so it became an incredible test for string theory.
So you were referring to the fact that Hawking asserted by looking at quantum mechanics around a black hole that the black hole could steal some quantum particles from empty space, leaving others free to radiate.
So yeah, he essentially he discovered that black holes actually aren't black. So
right.
String theory, string theory isn't the theory of strings. Black holes aren't black. Yeah.
I hope it's all clear now.
Right.
No, but what Hawking did.
Okay. Oh yeah. So, and I'm sure you'll take this in an interesting direction, but let me finish the point. Here, this opportunity to put together, if you like, a little bit of our understanding of quantum physics in the 70s and a little bit of our understanding of how that would work quantum mechanically, told you a very robust result about not just that black holes are black, but they're black in a very specific way. They radiate in a particular way, and they have a certain property that you should, in a full theory of quantum gravity, if you ever had one, be able to calculate. And you'd either get that right or wrong.
Right, so basically they're hot. We know how hot they should be. They should be radiating, emitting, and they're actually quite cold, basically. Most astrophysical black holes are quite cold. The bigger the black hole, the colder.
But there's a temperature you can compute.
But there's a temperature you can compute, and you're saying in string theory, your task is go compute that temperature if you assume that string theory is correct, and do you get it right?
So
Not the temperature, the entropy.
Yeah. So it turns out that it isn't quite the temperature, but it's a related thermodynamic property called the entropy. And I'm sure you knew that, but temperature is more accessible. Yeah.
Exactly.
So there's a thermodynamic property. There's a relationship. Okay. So there's an entropy. It's a thermodynamic property which all ordinary substances you can associate with it. It turns out magically, it seems, for a black hole, there's a geometric property which is essentially the area. If you think of the black hole as a ball, that's like there's an area you can compute of that ball. And you divide that area by 4, and in the right units, that's the entropy. And it seems like a magical result. It's very robust. And then the challenge is, if anyone writes down a quantum theory of gravity, the test of that quantum theory of gravity being on the right track is that they get that right. And so string theory could have failed at that point. And it took a long time to find the right way of doing that computation honestly. And finally, in 1995, Strominger and Vafa actually did that, and they got the number on the nose, and that was sort of amazing.
For one special, yeah.
For one special.
But what Hawking, the reason I think what Hawking really did was pose a challenge to quantum mechanics. So he found, he claimed, a conflict between the geometrical way of looking at the world, a la Einstein, and quantum mechanics. Because black holes, so black holes always had this problem. You throw stuff in a black hole, and you can't get out. That's what a black hole is, a region of space where there's so much energy density, that light you shine, try to send out, falls back. So you can't communicate with what's inside the black hole. So you throw a dictionary, and you throw Shakespeare's complete works into the black hole, and you've lost that information forever. Now, that is weird, but so
Big
what?
deal.
The information is there in the black hole, you just can't get it, right? But Hawking came along and said black holes behave like hot objects, and they radiate away their energy, their mass, and eventually they disappear. And now you're left with a situation with the black hole has radiated away all of its energy, nothing is left. What happened to the information? What happened to poor Shakespeare? And that violates the principles of quantum mechanics. In quantum mechanics, you don't lose information. You might lose your hair, but you don't lose information. So Hawking said, and if that can happen inside black holes, it can happen virtually. There could be virtual black holes popping out of the vacuum and disappearing. And in everyday experiments, not involving black holes, he claimed you would also violate the laws of quantum mechanics. You'd lose information. Now, he came from a community where geometry was king. There's a general relativity. People on my side of the fence who were doing particle physics believed in quantum mechanics. And we said, no way. And there was this quarrel and disagreement among these two communities for years. This,
For 40 years.
For 40 years, roughly. I mean, the relativist said, general relativity is so beautiful, you'll just have to modify quantum mechanics. And particle physicists said, quantum mechanics works so well, you'll have to modify gravity, Einstein's equations. So who do you think won? Well, I wouldn't be telling the story unless we won, and string theory played an important role in this because of exactly these dualities. There are now a whole host of cases, not our real world, of course, but simplified models, but they have black holes. And they can be mapped by these dualities, which we totally believe in, enormous evidence that they're correct, to simple quantum mechanical systems where there's absolutely no question that information is not lost. So although we don't understand a lot of the aspects of black holes and are still studying them, we know for certain that information isn't lost in this process. Stuff falls into a black hole evaporates, information gets out by quantum processes, which are still a subject of investigation. Hawking has given up. He agrees. He's conceded. So we won.
Yes, but you may have won, but every once in a while, a new debate breaks out which says, wait a minute, I don't understand how we won.
Yeah.
Even by some of your own proponents.
Exactly.
And in fact, this was the anecdote, David, I was going to tell you.
Absolutely.
I was visiting your institute a few years ago, and you walked up to Joel Polchinski in the hallway outside my office, and you say to Joe, who's a very famous string theorist, Joe, did it go away yet? Which was a problem with the winning side. And Joe said, no, man, it just hasn't gone away yet. And I came out to talk to you, and this was a very recent crisis which broke out where people didn't suddenly understand the resolution they thought they had, which made it look like string theory won.
Right. So, true, and yet. Nobody thinks that we lose information. There are, however, issues.
So we
involved.
won because we believe we can lose
No, you see,
Some would say we
what
won
is-
because there are more of
there are
us.
other
but-
weird. There are other many weird questions you can ask about black holes, and One of them is, what does it feel like to fall into a black hole? That's the question that Joe and others started investigating in detail. They said, after all, if string theory can give an account. So string theory resolved the issue that luckily you and I face, that we don't fall into a black hole. We just observe it from the outside. We do experiments. We throw stuff in. We wait long enough. We don't lose information. Everyone agrees with that. What still is unclear is what happens if you fall into a black hole, God forbid. You can't tell me anything, but what do you feel? Now, I'm on the outside, I don't particularly care, but
Yeah.
but for you falling in, it's an interesting question.
Right.
Maybe.
Do I see nothing because it's just
It's such a big black hole.
such a big black hole? It looks like I'm floating in empty space. I don't notice anything strange.
Or do you hit a firewall?
Do I hit a stringy mess piled
Exactly.
up on the outside of the horizon? Clifford, do you have an
Or
opinion
is
about
there
this?
any inside?
Or is there no
Some
insight?
people
So now we're going to get to emergence.
So that's the issue, and
Yeah.
I think we keep every decade or so a huge discussion breaks out, and lots of calculations are written and done, and lots of papers are written, and then we all work on something else for a while, and then 10 years later, here we are again, sometimes writing exactly the same papers because it's confusing. At the core of the problem is that while string theory is a theory of quantum gravity and seems very robust, we are certainly not we don't know what the right variables are, the right things to ask the questions of, to answer the kinds of questions we want to answer. And so we don't understand the toolbox well enough. So sometimes we're not using the right tools, and so the papers that get written are sort of not perfect, and they make arguments that have holes, what have you. One of the things that I think is crucial, and it's the whole business of whether or not a black hole really exists. And one resolution to the whole thing is that a black hole is just an approximation. And we shouldn't be surprised by this because we're learning that the whole space-time game is an approximation in some sense. It's an emergent thing. And so one possibility, which actually was hinted at in string theory way back in the mid-90s, but most of us didn't pay attention, with the exception of Samir Mathur, who really followed this through, is that there are clues about what the fate of a black hole is in a theory of quantum gravity like string theory. And the clues lead you to believe that actually a black hole is really this, although it looks like the simplest object in the universe from the point of view of a solution to Einstein's equations, it actually is in a way the most complicated object. It's made of all kinds of stringy, fuzzy stuff, which actually are called fuzzballs, is the term.
Very sophisticated term.
If you actually write models down of how that stuff works, you can model everything we've learned about black holes. For example, processes involving falling into a black hole and the time it takes to fall into a black hole and what have you can also be modeled by getting tangled up in all of that fuzz as you go in and stuff like that. And so it's very hard to do the computations, but the string theory actually tells the same success that I told you about earlier that counted that entropy, right, and got that gold standard test of string theory and black holes correct. If you follow your nose, it tells you how the same calculational tools give you the setup for what's now this fuzzball picture is. So the picture might be that the paradoxes that you run into if you assume Einstein's general relativity is correct, and there's this horizon, this one-way wall, this one-way barrier, and then you sprinkle in some quantum mechanics and you try and describe that quantum mechanically, and you run into all of these paradoxes when you start trying to fall into the black hole. Those paradoxes simply go away if you realize that whole picture is an approximation. And it's just that the physics in the right regime, especially for the observer outside, it just pretends to be this simple object with a one-way barrier.
So maybe there's no interior to the black hole
quantum mechanically,
whatsoever.
there's nothing inside. It's actually not.
Well, there had to be, black hole can't be a simple object because as you just pointed out, it has this humongous entropy.
Right.
And the entropy is simply related to the number of possible
Yeah.
states.
So that was the clue from
So-
the 90s. Yeah.
Well, yeah, so the black hole is kind of a coarse-grained description of what a
Yeah.
black hole looks like, of
Yeah.
what any one of this billions and trillions of billions of possible objects,
Yeah.
collapsed objects,
So-
looks like far away.
So Einstein's equations in 1915, before we understood the quantum structure of space-time, before we understood black holes and all of those things, which we must understand quantum mechanically, Einstein's equations did a really clever thing in this, if this is correct, which is that it said for a lot of questions, it's not the quantum structure of space-time and black holes and all of that stuff, which you're going to discover many years from now, won't matter, and I can just replace the answer to those questions with this simple thing, which is the Schwarzschild solution, the black hole solution that was discovered soon after Einstein's equations were discovered. And it's this beautiful, simple, simplest thing in the universe. And the equation... wait, let me finish.
Singular.
Let me finish the sentence.
Singular.
It is singular.
Yeah. Let me finish the sentence. And there are things in the and by coming up with that beautiful approximation that answers lots of things, including pretty much any question we can so far answer with these real experiments that are detecting gravitational waves, that's all you need. So it's, again, pragmatism. It's a great tool. But when you start asking quantum mechanical questions of certain kinds of black holes, simply don't use that tool anymore. There is no interior. There is no singularity.
Yes.
It's a fuzzy blob.
I love this conversation, and I could do this for hours, but luckily you gave me your watch, and I'm conscious of the fact that I want to open it to Q&A, but before I do, I really want to ask David to respond to this idea that maybe the black hole is only exterior.
I love fuzzballs. In fact, I had a long conversation with Clifford on the airplane. I think I convinced, but he has a colleague, one of the pioneers in the fuzzball, whom he didn't mention, Nick Warner,
Right.
who is finding more and more non-singular solutions of
Nick Warner
string.
in California?
Nick
Yeah,
Warner.
he's
yes.
I think he taught me general relativity.
Oh, right.
Yeah, he was
there
my
you go.
GR
sure
professor.
he's a
Was
good
this at MIT?
Yeah.
Yeah, that's Nick. Yeah, Samir Mathur came up with the idea and started working out in beautiful detail some of the simple models, but the challenge is to find all of the different kinds of solutions that make up that fuzzball, and Nick is an expert in finding those
He
solutions.
is a fascinating thinker, beautiful thinker. But I wanted to just ask you, David, if you could extend this into the idea of the emergence, and then we're going to open up to Q&A. How gravity might not be really fundamental, but
Well,
might
black
actually
holes
emerge.
is certainly one place. So as I said, the clinching argument that black holes, quantum gravity does not require changing quantum mechanics came from the duality of string theory situations where there are black holes and ordinary quantum mechanical systems which preserve information. So in principle, we can start with those ordinary quantum mechanical systems and say everything about a black hole. In practice, that's not so easy. And so the exploration along the direction that Clifford discussed of trying to really resolve the issue about what is inside a black hole, is there really a horizon, et cetera, is being approached by having this very strong duality, trying to answer this question within that framework. Hasn't yet been done. I have no problem. I think it'll be resolved more along the fuzzball line than anything else. For me, much more interesting about things that emergent space-time might resolve, go to one of the place you started, and didn't, and eventually if you kept pushing to lower scales, namely the large-scale structure of the universe, the end of the universe, and the very beginning. That's, again, from Einsteinian gravity cosmology point of view, where everything breaks down in a much more serious way than black holes.
So it's another terrain for us to study the
It's
fundamental.
another place where, I've always felt that how space and time began, the beginning of the universe, is not a question that one can formulate correctly within the current framework of our understanding of space and time, and that we're much more likely to be able not to answer the question of how the universe began, the initial condition, but to formulate the question correctly with a better idea, a better solid basis, not solid basis, a better starting point for space and time. That we don't yet know how to formulate the question. Therefore, we can't even imagine what an answer would look like.
Until we know how to actually ask the question properly.
Correctly.
It's a beautiful place to end the conversation before we open it up for Q&A. Can we please thank our guests for...
Let me just say before
David has a question.
The questions begin, and maybe to help me myself, let me thank the audience. I mean, this is, I always, I feel my audience. This is an incredible audience. Thank you.
Woo! We do. There should be microphones running around. Could you keep those microphones moving? We have a question over here. And I'm sorry, we always run over a little bit, so we'll try to take at least a few questions. Oh, and just actually before the first question, while the mic is going around, we have at least one or two string theorists who will be on the ground after the conversation holding up the postcard, so you can go talk to them and interrogate them about your questions that don't get answered here. Yes. It's called the string theory speakeasy, but I don't know, it might only be one person. Okay.
Hi. Okay, it's working. I want to give you my theory of the universe in a T-shirt format, basically.
Yeah, I'm timing this.
And then I have a question that relates to black holes, basically. So I think at the beginning there was just consciousness, yeah? So there was basically infinite energy in not zero space, but 1 divided by infinity space, yeah? And that consciousness wanted to experience existence, yeah? So it kind of, through a Big Bang, which is like an orgasm, created life, yeah?
You said that like we all agree.
Yeah.
We're all like,
So, but
wait,
now...
listen, I love your theory, but I have to keep it to questions.
No, yeah, of course,
no. So please, actual
basically
question.
what happens now is this infinite energy is distributing itself into 1 divided by infinity energy particles to infinity, which is the universe is still expanding, whatever. I think there's an inherent flaw in mathematics that when we multiply something by 0, it disappears. That's why we have black holes in physics. It's because it's not 0, it's 1 divided by infinity. It's close to 0, but it's not 0. So because I think nature is trying to show us what we can learn, and I want to hear your opinion on that, on 0 basically.
I'm gonna try to reframe this a little bit, which is that there's nothing wrong with black holes, by the way, mathematically on the outside. They're absolutely on completely solid mathematical ground. There's no infinities, there's no zeros, there's no confusion, there's no problem until we get to this quantum level. It's at the interior that you have something peculiar, but as we're discussing, and as David said in the very beginning of the conversation, that's a clue that something in our current framework is wrong. And we take that clue seriously that something is wrong. And that's what drives us to think about these other things. David?
Your theory is much too complicated for me to understand, but I found it fascinating that you were in contemplating the structure of the physical universe, you started with the simplest of all possible things, namely consciousness.
Do you have a feeling about infinities and mathematical breakdown? You're not okay with singularities, I'm assuming.
No, I usually, when we're doing calculations in physics, if you find infinity, it's usually a sign that you don't have everything on the page yet. And it's usually, sometimes it can be a healthy indicator to investigate further, and there are many good historical examples of that. So in that broad sense, you're on the right track, but the devil's in the details.
Is that mic still moving? Whoever has a mic can pop up.
hands, but
Yeah.
no mic.
Can we get, I think we might have another mic in motion. So I think we have someone over here, and then we'll come to you. I think we have someone over here, yes?
Okay. I'm wondering whether...
Then you. Yeah.
Okay. Is it really physics to consider the breakdown of space and time, since physics is the measuring of things within space and time?
Space and time, as I said, are not... Think about space and time. Where did you hear about them? They're mental constructs. They're tools for understanding the world. And all of our tools for understanding the world have been modified over the years, even space-time. And, for an infant and for Newton, time existed throughout the universe, and events were, any two events that happened were either one preceded the other or one came before the other. That's not true in Einstein's theory of special relativity. The space-time structure, the geometry of the world before Einstein's theory of general relativity was rigid and immovable, non-dynamical, just out there, a framework. That's changed after Einstein's theory of general relativity. So space and time are part of our theory of the world.
Yeah.
You constructed yourself as an infant, but they're not God-given or a priori necessary concepts in their present form, and are changing. And we're now exploring how they're changing in very profound ways.
Yeah, that's been one of the biggest changes. And so, indeed, I think the questioner is in some sense expressing something that would have been extremely reasonable to say until relatively recently. And relatively recently in the scheme of doing physics over the last however many thousands of years. And the point, just to mention my book, I should.
Which he'll be signing after
available.
the talk.
All good book stuff.
The book table's over here.
The point, the way I like to put it is that you have the game and you have an arena. Right, and for a long time, all the physics we've been doing was about the game, the rules of whatever game's taking place. And it's in this stadium, and you don't worry about the stadium changing shape during the middle of the game. So there are no rules for the stadium. And then Einstein came along and said, oh, the stadium also can change with the game. And the game actually affects the stadium, and the stadium starts moving.
Then it
and
gets
so you need
complicated.
rules for the stadium as well. And that stadium is space and time. And that becomes a real physical object. And so just as we encounter infinite breakdowns of physics descriptions in the game, we can now encounter breakdowns in our description of the arena. And that doesn't mean that something broke. It means we need to understand it better. We need to understand the physics better. And so that's what this whole business is about. The physics of space-time is just as amenable to the laws of physics as anything else. Yeah.
And
I think that was it. Oh.
Sorry, there's a question at the end here. Thank you, James. Yeah.
Thank you. This is a much more pop question, and I'm thinking back on when you were talking about how you can't just turn left into the wrong dimension, and you were talking. Sorry, hi Clifford. You were saying that maybe these other dimensions are too large or too small, or we're just not probing them with the right kind of stuff. So how would you respond to the kind of sci-fi theory that you hear that, in fact, they are just the right size, and we just don't know that we're moving between them all the time? And how can you respond to that in a way that maybe also isn't just of the flatland style, where we just don't understand these other dimensions? Like, what is the possibility of that?
The response is give me the evidence, right? The job of science isn't to sort of shut down imagination and ideas like that, but what science does ask is that you give me some evidence. So if someone comes along and says, no, they're just the right size, as you say, and I'm moving back and forth between them all the time, and that's where I keep my stuff or whatever, fine. And you go, okay, well, show me.
That's where my keys are.
Right, that's where my keys are. Exactly, right. That's where all those odd socks are. There's another dimension. Right, yeah. So the answer is, okay, fine. So demonstrate that. And so until someone actually comes along and shows you in a reproducible way, and this is why science is wonderful. This is why science is one of the most awesome democratic things we've ever invented, or because it means that everybody should be able to, in their own way, with their own kinds of experiments, demonstrate the existence of these extra dimensions that this person is going back and forth. So until someone can do that, there's, or shows that there's some physical phenomenon in the universe that would not be explained without those things, then there's no evidence for it, because that's how science works.
Can I try an example? So let's say you insisted to me that there were no dimensions beyond 2. I could just very easily walk upstairs and defy your condition that there were only 2 dimensions. I just don't seem to be able to do that. And we would know if we could. So in fact...
And it's not that people haven't tried. People have proposed ways of discovering these extra dimensions. And then they did the experiments, and they didn't find it.
I
Now,
think dark energy is from extra dimensions, actually. Seriously. So we might observe it, and we don't know yet.
Yeah.
Could be,
Yeah.
but you know, we need some evidence.
Yeah. So that's one of the things. That's one of the things the program is doing. In that, one depressing thing that you may go home with, but don't, is the fact that it would take just an unimaginable amount of technology and to build the giant accelerator that would find these structures directly. But the point
curse
is
of the logarithms.
But the curse of the logarithms. That's a book title. We was trying. Yeah. The one possibility is that there are other sort of indirect consequences of these ideas that may be staring us in the face. Maybe we're looking up in the sky and there's a thing yelling at us, extra dimensions, or
dark matter or vibrations from the extra dimensional modes.
It might be dark matter, it might be dark energy, it might be other things. It might be those patterns in the standard model that that we don't yet understand. And there actually are toy models of string theory that tell you, if those models were correct, why you have 3 families that look the same, and it is to do with extra dimensions.
Yes, that's right.
That's
lovely.
As toy models, those aren't real models, although some people think they're real. But the point is that there are indirect consequences of these ideas, and that's actually our best hope for understanding a lot of these kinds of things.
So maybe we
but
are
to your
seeing
question, yes, it would be, if someone says these dimensions already exist, your response is, what's the evidence?
So I know we have I think we can only do about 2 more questions. You have a microphone here? Yeah.
Hi, I was wondering, in your analogy for information being lost in a black hole, with the Shakespeare and everything, what exactly entails like information being lost? Is it the breakdown of the matter, or is it the ideas being canceled out somehow?
So, well, it's really information. Actually, you know, it's fascinating. Information is a concept which till now has sort of played very little role in physics, but is coming rapidly to the forefront. We're very interested now in the information content of a state in quantum mechanics, in a quantum mechanical system. So what is really meant by information is the ability to make predictions, okay? So if you have a complete, with the limitations of quantum mechanics, but if you have physicists, or the business of physics, if you want, is to, given the present, predict the future. We're in the predictive game. We test our ideas by their ability to make correct predictions. Now, there are, if you lose information, then you lose the ability to make predictions. So what would happen if Hawking had been right is there are a lot of these black holes around which could suck up information, or virtual black holes, even worse, that pop into being, suck up information, then disappear. You would find that would greatly limit the ability of physicists, no matter how good his theory was, the basic structure of the world would be such that you wouldn't be able to make arbitrarily good predictions of the future, given what you know in the present. And boy, that would be disappointing to a physicist, because we're a greedy, arrogant lot.
We have a question, sorry, with the microphone.
Hello?
Yes.
Yes. So I first wanted to say thank you. I thought this was absolutely fascinating. I was struck by the recurrent use of aesthetic categories in what you're talking. Theories are beautiful, sometimes they're elegant. And I was wondering, what is the criterion of beauty here? If I think about it, it seems that you seem to think that reducing to one, unifying is beautiful. What's so beautiful about unifying stuff? What if it was an antinomic universe? Maybe that's more beautiful. Why are you so convinced that a beautiful theory is one that unifies?
So I've thought about this a lot. What is beauty? So scientists often say, well, and it's true, that the universe, our understanding of the universe is beautiful. Mathematicians also say that. They say a theorem or a mathematical concept structure is beautiful. Very hard to explain, as you know, beauty to somebody. You either get it or you don't, right? It's about all aspects. But I believe that there's a kind of evolutionary basis for our concepts of beauty. Evolutionary psychologists, biologists argue that our concepts of beauty, of people, of art, even of music, are evolved. I mean, we're not just arbitrary objects, and we've evolved. One of the things we evolved to do, and develop this thing, especially our species, is to understand and control the real world. We're pretty good at it, better than other species. That's why we're killing them off, right? Because we've learned to control the world. So our brains have evolved to understand in order to control the real physical world. Is it therefore surprising that when we discover mental structures that allow us to understand the real world, our brain doesn't have a mechanism for giving us a dopamine kick and finding that enjoyable and beautiful? I think it's quite reasonable. In fact, wouldn't it be even weirder, if we were to discover some beautiful mathematical construct or physical theory that worked and was ugly? So I'm not surprised at all that
Please.
we have evolved in order to understand the real world and find our explanations that work beautiful.
So, that's great. So I would add to that something which I keep coming back to, which is that I think it's important to reflect on our history of how we've made progress in the past. And so that, again, it's pragmatism. An aesthetic view, and it doesn't mean one aesthetic view that everyone has to agree with, but some kind of aesthetic guidance has been extremely powerful in making breakthroughs in many instances in the past in this field or related fields. And so, especially when we don't have direct guidance from experiment, it is something that has been reliable in the past, and so it's sort of the first thing you might then reach for if you've got nothing else. And they're great examples. Einstein, of course, Dirac, one of my heroes, I think, in terms of being
Strange
led,
dude.
Yeah, being led to the equation that describes the electron in a way that was completely aesthetic. And extremely, there's Graham Farmello's wonderful book, The Strangest Man, is a wonderful book. I recommend that. And there's so many other examples where an aesthetic sense, even if it's sort of wrong in the big picture, as a guide, can be very useful.
I think that's I know there's so many wonderful questions, and Clifford's going to be at the table to answer some. I'm going to whisk David off, but that is a beautiful place to end the conversation, which is on beauty. Please let's thank our speakers again.